In the previous class, we looked at friction choking and its consequences. So, in the subsonic and the supersonic case, if the Mach number m1 is such that the L star corresponding to that m1 is less than the length of the duct L, then friction choking occurs. And we said that if friction choking occurs depending upon the length of the duct in comparison to L star, in the subsonic case the mass flow rate is adjusted. So, if for example L is greater than L star corresponding to the given inlet Mach number, then if the Mach number m1 is less than 1, m dot changes. So, we saw that in the subsonic case the mass flow rate through the duct changes to accommodate the new length. So, m dot changes, so that such that the L star corresponding to the new one. So, L is equal to L star corresponding to the new operating condition, and if the Mach number initial, the inlet Mach number is supersonic, if m1 is greater than 1, then a normal shock occurs in the duct. So, the location of the normal shock has to be determined iteratively. We will work out a numerical example that illustrates how this iterative process works. We will look at both the cases through worked examples. So, now we take a look at calculation procedure. How do we do practical calculations using the theory that we have developed so far. So, calculation procedure here is the same as what we did for Fanno flow. So, if you remember from our governing equations, we had written down rho 1 u1 is equal to rho 2 u2, and if I substitute for rho 1 in terms of P1, so I can write this as P1 over RT1, and for u1 I can substitute in terms of Mach number and the speed of sound. So, this is m1 times square root of gamma RT1, that is equal to P2 over RT2 times m2 times square root of gamma r T2, and if I rearrange this, I get P2 over P1 is equal to m1 over m2 times square root of T2 over T1. Now, in this particular flow there is no heat addition, so stagnation temperature remains constant. So, we can write this as, since T naught is equal to T1 times 1 plus gamma minus 1 over 2 times m1 square, and this is also equal to T2 times 1 plus gamma minus 1 over 2 times m2 square. So, I can write T2 over T1 as follows: T2 over T1 is equal to 1 plus gamma minus 1 over 2 times m1 square divided by 1 plus gamma minus 1 over 2 times m2 square. And I can actually substitute for T2 over T1 from here into this equation. So, I still have T2 over T1 in the right hand side. So, if I substitute from there, I can get P2 over P1 to be equal to M1 over M2 times square root of 1 plus gamma minus 1 over 2 times M1 square divided by 1 plus gamma minus 1 over 2 times M2 square. And I can write P02 over P01 in the same way as we did earlier. So, P02 over P01. Remember, this is a flow with friction, which is an irreversibility. So, the entropy increases and there is a loss of stagnation pressure as a result of the increase of entropy. So, P02 over P01 can be written as P02 over P2 times P2 over P1 times P1 over P01. And you know that P02 over P2 is nothing but 1 plus gamma minus 1 over 2 times M2 square raised to the power gamma over gamma minus 1, and P2 over P1 is given from here. So, this can be written as M1 over M2 times square root of 1 plus gamma minus 1 over 2 times M1 square divided by 1 plus gamma minus 1 over 2 times M2 square. And P01 over P1 is going to be 1 over 1 plus gamma minus 1 over 2 times M1 square raised to the power gamma minus 1. So, now we have all the quantities that we are looking for. M1 is known. So, if you look at these 4 expressions, M1 is known, that is the Mach number at the inlet. If I know M2, then all the quantities that I need are known. Okay. So, we calculate M2 from the momentum equation. So, we do something like this. So, we start with the differential form of the momentum equation. So, you can write the momentum equation in differential form like this. If you take a small control volume and write the differential form of the momentum equation, it looks like this. F is the friction factor. Remember, F is the Darcy friction factor. Please remember that. And if I make use of the equation of state and the definition of Mach number, I can write this as dP plus P over RT times m square times gamma RT times du over u. Notice that I have multiplied and divided this term by a u. So, I get a u square here and a du over u. So, u square can be written as m square times square root of m square times gamma RT, right. And I have done the same thing here, 4 over dH times 1/2 times P over RT times, again u square is m square times square root of gamma RT times f dx equal to 0. Oh, I am sorry, this is m square times gamma RT, the square root disappears, right. So, there is no square root here. So, you can easily see that the RT cancels out in both these terms and the P can be brought to the denominator. So, I end up with an equation that looks like this, dP over P plus gamma m square times du over u plus 4f over dH times gamma m square over 2 times dx equal to 0. And we derived relationships earlier for dP over P and du over u in terms of dm over m. So, if you use those relationships, so eliminate dP over P and du over u in favor of dm over m. So, we can get a relationship that looks like this. So I am going to leave the algebra to you. So I will just write down the final expression. It is m square minus 1 over gamma m square times 1 over 1 plus gamma minus 1 over 2 times m square times dm square over m square equal to minus 4f over dh times dx. So this equation that we have written down finally gives me an expression involving duct length and change of Mach number. Okay. So I have two ways in which I can proceed now, just like we discussed earlier. If I have a duct of length, let us say L, and this is state 1, this is state 2, m1 is known here, right. I can integrate this equation, left hand side from m1 to some m2 which is not known, and the right hand side can be integrated from 0 to L. So that will give me L, right. So right hand side dx when integrated from 0 to L will give me L. So I will have a highly nonlinear equation involving m2 from the left hand side. I can solve that and get m2. Now this means I have to solve a nonlinear equation every time, and so I need to have very complex tables. The other problem is such nonlinear equations also have multiple solutions. So we avoid this by using the same trick that we used before. So what I am going to do is I am going to take a certain value of m1 and integrate from some that m1 to m equal to 1. So the right hand side, if I do that, will give me L star corresponding to that Mach number, right. So let me write this down and then we will see. So the left hand side I am going to integrate from some m equal to m1 to m equal to 1. So this is m square minus 1 over gamma m square times 1 over 1 plus dm square over m square is equal to minus 4f over dh times, in this case this becomes the L star corresponding to m1, right. Notice that we are assuming that the friction factor F is constant along the length of the duct. In fact, we are not accounting for variations in the friction factor. Usually for these problems you will notice that for the kind of Reynolds number that we are operating at, friction factors will not vary significantly. So this is a very good engineering assumption. So this is L star corresponding to m1. Notice that now I am not solving an equation, I am just obtaining this integral. This can actually be evaluated in closed form. So what I do is, so I take m1 to be 0.1, 0.2, 0.3, 0.4, so I tabulate this for all values of subsonic Mach numbers. I do the same thing for supersonic Mach numbers also, right. I can start from 1.1, 1.2, so I tabulate this, then I do not have to solve the equation. So if I know an m1, I calculate L star corresponding to that m1, right. So L star corresponding to that m1 may be something like this, right. So this may be L star corresponding to m1. But because we are operating on the same branch of the Fanno curve, this is nothing but L star corresponding to m2, right. So, with the known value of M1, I calculate L star. From this tabulation, I know L star corresponding to M1. I subtract the length of the duct, I get L star corresponding to M2. So, I go to the table again and see what is the value of M2 which corresponds to this value of L star. That is the basis for the calculation procedure, same as what we did for Rayleigh flow also. Okay. So, it is tabulated, we do not have to solve any equations at all. It is a very effective way of doing calculations, and that is what we are going to do. We are going to use this table to do these calculations. Okay. Any questions before we do that?
All these frictions will depend only on hydraulic diameter, or will it depend on the aspect ratio?
The friction coefficients depend upon primarily upon the or depend only upon the Reynolds number. The friction stress depends upon the hydraulic diameter, but the friction factor depends only on the Reynolds number. Okay. And you will notice that for the kind of speeds with which we are working, the Reynolds number based on hydraulic diameter will be so high that you are essentially operating in a region where the friction factors are constant. So, in fact, you are far to the right on the Moody's chart, where you notice that the friction factor is independent of Reynolds number. That is the kind of region that we are operating in. So, that is a very good engineering approximation to use. Okay, let us do a worked example next. We will do two worked examples in this module, one for a subsonic entry Mach number, another one for a supersonic entry Mach number. And in both cases, we will look at situations when L is less than L star and L is also greater than L star. Okay. So, the first example that we are going to do reads like this: air enters a 3 centimeter diameter pipe with a stagnation pressure and temperature of 100 kilopascal and 300 Kelvin and a velocity of 100 meter per second. Compute A, the mass flow rate, B, the maximum pipe length for this mass flow rate, and C, mass flow rate for a pipe length of 14.5 meters. Take F to be 0.02 for the calculation. So, let us write down the information here. So, this is, let us call this worked example 1. So, we are given a pipe, the diameter of the pipe is given to be 3 centimeters, friction factor F is given to be 0.02. Remember, this is Darcy friction factor, and at entry to the duct, so this is state 1, we have been given P01 is equal to 100, T01 is equal to 300 Kelvin, and U1 is given to be 100 meter per second. So, we are asked to calculate first the mass flow rate m dot through the pipe. So, to calculate mass flow rate, we need to know the static conditions. Stagnation conditions are given here. So, let us start with the static conditions. So, T1 is going to be T01 minus U1 square over 2 Cp, and if you substitute the numbers that are given here for T01 U and U1, and we will also say that the molecular weight, we will use molecular weight for air to be 28.8 kg per kmol, and gamma for air to be 1.4. So, if you substitute these numbers, we get the static temperature to be 295 Kelvin. And the static pressure P1 is nothing but P01 divided by T01 divided by T1 raised to the power gamma minus 1 over gamma, I am sorry, gamma over gamma minus 1. And so, the static pressure comes out to be 94 kilopascal. So, the mass flow rate m dot is rho 1 A1 times U1, and rho 1 is nothing but P1 over RT1 times A1 times U1. So, all the quantities are known in this. A1 is nothing but pi d square over 4, where d is the diameter of the duct. So, if you plug in the numbers, you get the mass flow rate to be 0.078 kg per second for part A. Now, part B asks us to determine the maximum length of the pipe that I can have for this mass flow rate. So, the maximum length is going to be equal to L star corresponding to the inlet Mach number. So, let us look at part B. So, part B, for the mass flow rate to remain the same, the maximum length that I can have is L star corresponding to M1. And M1 we can calculate like this: M1 is equal to U1 divided by square root of gamma R T1, and this comes out to be roughly 0.29. So, we have to use the tables for this. So, let us look at the tables. So, we are now using table D, which corresponds to Fanno Flow, and you will notice that the table lists data like this. Mach number, for each Mach number you get all the quantities that you want, right? P over P star, T over T star, rho over rho star, P0 over P0 star, and FL star over DH. Okay. So, now our Mach number is 0.29. So, let us see. So, corresponding to 0.29, which is over here, FL star over DH is 5.79891, right. Let us write this down. So, corresponding to, so for M1 equal to 0.29, FL star over DH comes out to be approximately 5.8, right. Let us use 5.8 for this. So, from which I can calculate my L star corresponding to this Mach number to be about 8.742 meters. Yes.
So, when to use 4 FL L star by D and only F?
I have consistently said throughout that we are using the Darcy friction factor. Okay. Now, in the aerospace community, they use a friction factor called Manning friction factor, which is actually off from this number by a factor of 4. But Darcy friction factor is the most widely used friction factor in connection with flow through pipes and ducts and so on. So, that is what we are using. Okay. That is why you do not see the 4F there. So, the Manning friction factor for the same case, okay, instead of F being 0.02, the Manning friction factor for this case would have been 0.005. So, that 4 times that is equal to this. But Darcy friction factor is the most widely used, all the correlations give only this, which is why we are using this. Okay. Please note that when you are using the Darcy friction factor, you should not use tables that have the last column as 4 FL star over DH. If you see 4 FL star over DH in the last column, notice that the last column in the table that we are using is FL star over DH. The last column is 4 FL star over DH. That would usually mean that the F that is being used there is the Manning friction factor and not the Darcy friction factor. So, this tells me that the maximum length that I can have for this mass flow rate is 8.742 meters. So, if I use a 3 centimeter diameter pipe, so I have my experimental setup or some other device set up over here, and my compressed air tank is, let us say, further down. If the pipe length that I am using is more than 8 meters, then I will not get this mass flow rate. It has to be below 8.7 meters for me to get the same mass flow rate that I am looking for. Okay. Part C of the question says, what would be the mass flow rate if the length of the pipe is 14.5 meters, more than this maximum value, that is part C. So, part C, m dot equal to what if L is equal to 14.5 meters. So, now since L is greater than L star corresponding to m1, which is 0.29, we expect the mass flow rate to decrease and the inlet conditions to be different, right. Since L is greater than L star, we expect the inlet static state to change to a new state, which we are going to call as, let us say, 1 prime, such that L star corresponding to m1 prime is equal to L. And again, we have not been given any information about the exit pressure. If exit pressure is specified, then we need to determine an inlet static state which is such that the pressure at the exit of the duct matches the exit ambient pressure. Since nothing has been given, we will assume that it comes out at the sonic state. Okay. So, for the given length of 14.5, right, let us calculate FL over DH for this value comes out to be 0.02 times 14.5 centimeters divided by this is a pipe. So, you know that hydraulic diameter of the pipe is the same as the diameter of the pipe. So, this is that is 14.5 meters. So, this is 0.03 meters. So, if I go to the tables with this value, so this corresponds to m1 prime, which is equal to 0.24 from the table. Okay. So, the inlet Mach number changes from 0.29 to 0.24, but the stagnation conditions remain the same. So, T1 prime is equal to T01 divided by 1 plus gamma minus 1 over 2 times m1 prime square, and T01 remains the same. So, this comes out to be 297 Kelvin. And P1 prime can be calculated in the same manner as before, P01 divided by 1 plus gamma minus 1 over 2 times m1 prime square raised to the power gamma over gamma minus 1, and this comes out to be 96.1 kilopascal. Now, the velocity u1 prime is nothing but m1 prime times square root of gamma r t1 prime, and if you substitute the numbers, the velocity comes out to be 83.1 meter per second, slightly different from what we had before. Earlier we had 100 meter per second, now we have 83 meter per second. So the new m dot, let us call it m dot prime, is once again rho 1 a1, I am sorry, rho 1 prime a1 u1 prime, and that is nothing but p1 prime divided by r t1 prime times a1 times u1 prime, and this works out to 0.066 kilogram per second, which is a 15.4% reduction. So if you design a compressible equipment expecting certain inlet conditions, and if your pipe is, let us say, longer than, if you do not know the design and you just simply use a very long pipe, then the mass flow rate, as you can see, is going to be substantially different from what you are hoping to get. Okay, that is the reason why it is very important to study Fanno flow. The effect of friction can be quite significant, and the change in inlet condition is also quite significant. Notice that at the exit state now, if you are using a 15 meter long pipe, the exit state Mach number is 1, okay, whereas you might have designed the equipment for some other inlet Mach number, which is equipment which is connected to the end of the pipe. You may be expecting some Mach number and some mass flow rate, whereas the conditions are totally changed now. Okay. So if you want to use a longer pipe like this, then what you need to do to avoid friction choking is to increase the diameter of the pipe, use a larger diameter, and then design the flows pipes properly so that you get the conditions that you are looking for. Okay. So that is the worked example where we looked at the inlet state, subsonic inlet state. Okay. Next example that we are going to do, we will use a supersonic inlet state and then see how the changes take place. The next worked example reads as follows: air enters a 5 centimeter by 5 centimeter square duct at 300 Kelvin, 100 kilopascal, and a velocity of 905 meter per second. If the duct length is 2 meters, find the flow properties at the exit. Take F to be equal to 0.02. So here we are given a square duct right. So the cross section of the duct is square, 5 centimeter by 5 centimeter. F is given to be 0.02. The inlet state we are given we have been given the let us assume these to be static conditions since nothing is said. So, we take P1 to be 100 kPa, T1 to be 300 Kelvin and U1 is given to be 905 meter per second, and the hydraulic diameter, the cross section is given. So, the hydraulic diameter, if you remember, is 4 times the area divided by the perimeter. So, 4 times the cross sectional area divided by the perimeter for this case gives me the hydraulic diameter to be 5 centimeters again, coincidentally. Okay. Now, you may wonder how this can possibly happen in real life. Why would I want to have a flow that is entering at a Mach that's entering at let us say velocity of 905 meter per second into a duct? This can very easily happen if, for example, you are doing let us say supersonic flow experiments in a wind tunnel, right. So, we may have a nozzle which is connected to this may be your test section where you are going to keep some objects and other things that you want to test, let us say in a supersonic stream. So, in such cases you will definitely get these types of flow situations. So, it is very important that you study these types of flows. So, they do occur in real life. Okay. So, let us start with, since the static conditions are already given, we can calculate the initial Mach number m1 as u1 divided by square root of gamma r T1, and this I get to be 2.6. So, for m1 equal to 2.6, F L star divided by dH comes out from the table as, I am sorry, F L star over D from the table we can get to be 0.4526 from the table, from the Fanno table. So, this gives me L star corresponding to my Mach number m1 to be 0.4526 times dH divided by F, which comes out to be 1.1315 meter. And the problem statement stated that the length of the duct was 2 meters. Okay. Questions?
So that saying this gas table FL by D is 1.353.
Please look in the supersonic.
Yes, so the 2.6 Mach number. Or 1 gamma equals 1.2.
1.4.
Yeah, 1.4. 1.353.
No, what I have is correct. That may be 4 FL star. Yes. But we are not using that. We have to use a table which is which is FL star. We are using Darcy friction factor, not Fanno friction factor. So you have to be okay. 1.1315 meters. That is what we have used. Okay. So notice that what we have done here is we have gone to the Fanno table corresponding to 2.6. FL star comes out to be 0.4526. That is what we have used. Okay. So, since the given length L is greater than the L star corresponding to M1 and M1 is greater than 1, the inlet is supersonic, there is going to be a stance in the duct. So, we have to locate where the normal shock is and then determine the exit properties. Okay. We discussed this scenario in the previous class. Let us recap the scenario before we proceed with our calculations. Okay. So, we have a duct. So, this is state 1, this is state 2, this is L. Okay. Now, let us say this is L star corresponding to M1, right. Remember, L was, for this example, L was 2, but L star corresponding to M1 was less than L. So, let us say this is L star corresponding to M1. Okay. So, normal shock stands somewhere in the duct like this. Let us say that the state point just before the normal shock, let us call that X, and the state point just downstream of the normal shock, let us call that Y. Okay. Let us further state that the shock stands, let us say, at a distance Ls from the entrance of the duct. Okay. Now, state point 1 and state point X lie on the same branch of the Fanno curve, correct. So, since states 1 and X lie on the same branch, and that is the supersonic branch of the Fanno curve, L star corresponding to Mx is going to be L star corresponding to M1 minus Ls. Okay. So, that is one relationship that we have. Now, if no information about the exit is given, then we assume the exit states to be the sonic state. Okay. If you assume then notice that L star corresponding to My is nothing but total length minus Ls, that is the remaining length, right. So, this is L minus Ls, and that has become equal to L star now. So, if you assume the exit state to be the sonic state, then L star corresponding to My is L minus Ls. So, the calculation has to proceed iteratively now. We assume the shock to be at some location, that means Ls is known. So, then corresponding to M1 we calculate L star. Then since we have assumed a value for Ls, I can get L star of Mx. Corresponding to L star of Mx, from the supersonic part of the Fanno table, I calculate Mx. With the value of Mx, I go to normal shock table to get my My. With the value of My, I go to the subsonic part of the Fanno table to calculate my L star corresponding to My. I check to see whether this value is equal to this value. They are not equal, then I adjust the shock location, I use a different value for Ls and repeat the same thing. That is the procedure that we are going to use. So, we will write a table and then do these calculations in the next class.